Ah, hello, hello. Can you hear me okay? Oh, thank God. I was
Hey,
trying to.
Leo.
Hello, Robert. I'm not signed into my usual account and it was throwing all these messages at me saying I'm a bad person. I'm not permitted. And I thought, perfect, just perfect. Um,
Well,
and do we have.
that Ryzen rig behind you is not going to win you any friends here. So,
I have no friends anywhere. I'm so used to this. This is just 100% expected.
okay,
Yeah.
Um,
it's cool.
if you chaps could, is Mark in the background or is he not?
He hasn't joined yet, but I can do some quick setup. So Ori, background on this. Leo and I have known each other for a very long time. Great journalist. Has covered the PC industry for forever. Um, and unfortunately, he was not able to make it to ITT in Taiwan, so he did not get the live experience of your talk. And they wanted to learn more about the removal of SMT from the products, like why, what are the benefits of that, and this is an open conversation. Hey, Mark, welcome. I just did some setup, but if you have any opening remarks, Mark, that would be welcome. But that's the basic background of why we're here today.
Okay, uh, did you look at the recording of the talk?
I watched your talk, your conversation with Alejandro at the same
Okay,
time. So now I have to say that the SMT thing is of interest.
okay.
But since then, more things of more interest have come along, including Lipbu's presentation last night. Um, I'm not certain whether you and I actually had a conversation in Israel in 2022 for the first tech tour. I don't know whether you were part of that or not. You're half
Um,
familiar.
yeah, well, I was there, but I was not a keynote speaker. I wasn't at the front of the stage.
No,
So,
but were you on one of the round tables discussing Raptor
no, in
Cove?
2022, I was not.
The note I have is that you're Ori Lempel, you're a senior principal engineer in the core design team. Is that correct?
That sounds about right. Yes.
Excellent. Um, could we kick off? So, what I'd say is anything that you don't want to discuss or you aren't allowed to discuss or whatever it might be, or it's a dumb question, if you use the word something like either that's a dumb question or this is a better, more interesting thing,
So I
just
was taught that, yeah, I was taught that no question is a dumb question. But if there's something that I'm not comfortable discussing or I'm not allowed to discuss, I'm going to tell you. So you can ask whatever you
perfect.
want, and we'll see how it goes.
Perfect. As an opening question, how far ahead do you designers work when you're working on a core? And how much confidence do you have in whichever process you'll be using when it actually comes time to make your design into metal?
Okay, so let's see. What is the latest product that we have out on the market now? It's Lunar Lake, right?
Yeah.
Lunar
I
Narrow.
don't I don't know the marketing thing, but it's Lunar Lake has a Lion Cove P core.
Mm.
Okay. Right now, we are working on um, the grandchild of Panther Cove, actually the great grandchild. So it's three generations post Line Cove. That gives you a chance of how far ahead we're working.
Okay.
Okay, so um, there's one generation that is, I think that it's been disclosed. It sits on Panther Lake, which is the next like SoC that we're supposed to be shipping into the market in the second half of this year.
Uh-huh.
There's another which is already in production and in test, and we're now working on or we're executing the design of the subsequent generation to that. Now, we've done a fairly big shift in the way we architect and design our not only our cores but our SoCs, so that they are 99% process node agnostic, meaning they can be hardened on any process node in terms of, the libraries are there, the analogs are there, the design can synthesize to whichever process node basically we want to harden it to. Of course, the optimization is process node dependent because Intel processes, TSMC processes are all different in terms of parasitics, et cetera. So you have different power optimizations that you can do. You can push the thing to different frequencies. But basically, if say 5 years ago we would have designed our cores, especially, we've really optimized them to a certain Intel node, and that got us actually into trouble in the past where a certain process node got pushed out. We didn't have a product to tape out, right? Because we were really bound at the hip to a certain process node. We don't do that anymore. We actually dual and triple drive our products so that they can be hardened on a variety of process nodes. And the decision which process node to use on which product actually is a time to market versus a performance decision.
Does that still apply with Panther, where you're moving to 18A, which is backside power, and it's whatever you want to call it, not TriFET, not FinFETs, but instead you're moving to nanowires or whichever name you want to use for it?
So again, you remember that Lion Cove or Lunar Lake was only manufactured on TSMC process.
Sure.
Okay, and then Panther Lake will only be manufactured on Intel process. Subsequent products may be manufactured on both Intel and TSMC. Whatever makes sense for that product at that particular time.
And with Panther Lake in particular, as you say, you're working, where we're 25, I guess you're thinking in terms of 2028 or some such. But the changes for the processors that we're due to see, the SoCs we're due to see in the second half of this year, seem like a dramatic change to anything we've seen for years.
Yeah.
Is that a case of, I don't know if you know the pub game in this country, darts, hurling the darts at the dartboard. Have you basically got to score with every single dart to make the thing work correctly because you're changing so much?
So again, on the design side or the architecture side, not really, because again, we're architecting and designing the parts to be process node agnostic.
Okay.
We have a few physicists and chemists that are tasked with getting the thing to actually work as it should, meaning hitting its yield targets and performance targets. Okay.
Leo,
Again,
if I may, real quick, just
Sure.
the way to think about Panther Lake is it's basically a derivative of Lunar. It's evolved from Lunar Lake, and
Sure.
we know the market. I'm thinking about your readers here, what they want to see, and what they've been asking for. It essentially designed to combine the multi-thread of Arrow with the power of Lunar. I mean, that's a gross simplification, but that's the intent of the product.
It's beautifully put, though. Thank you. In terms of your design process, judging by your conversation with Alejandro, it seems as though you're told this is the product we're aiming towards, and now make a core and tell us how it works. And you have priorities, say power or performance.
That's how it always works. That's not new.
Right.
That's
so
how it. Yeah.
And you use P2P, performance to power, came up quite regularly in your conversation.
Yeah. Mm-hmm.
I'm hearing you saying P2P, and to me that just means efficiency. Is that the same as efficiency, or is there a subtle distinction I'm missing?
Well, PNP is basically how much performance you can suck out of the part at a given power envelope, or conversely, how efficient can this part run at a given performance point, right?
Okay.
So, and really, the way it always worked was you have a product architect. It doesn't really matter if it's a desktop product, a cloud deployment thing, a notebook, 15-watt part, 28-watt part, whatever. They basically give us being core people, the landing zone for that product, meaning you need to design a core that hits a certain, let's say, spec score or Sysmark score or Geekbench score, and at this power envelope. Okay, so you are given 4 watts per core. Go hit that benchmark score. Okay,
and historically,
just giving a broad characterization of things. Now, of course, this is like pink sky, everything works correctly. That's like the first silo, and then there's a give and take, right? Because there are always trade-offs. If you want to add capabilities to the core that don't translate into performance, but let's say security features or reliability features, or you want to have this fancy new ECC scheme, these all eat into your power budget, but don't really matter to a person running Geekbench, right? So there's all sorts of give and take, and then you need to consolidate all the requirements that you get from your different customers being different SoCs or products, and then you need to design something that hits or checks most of the boxes, and design it in such a way that it'll be easy to spin off derivatives that kind of take care of the outliers. Meaning, if you have a core that has to go into a desktop part that is really power unconstrained, and you can just fire away at 6 gig and consume 10 watts of power and you're all good, and it also has to fit in this thin and light fanless device that you're bound to a 1.5, that may not be a common design. It may need to be a derivative, but your superset design takes everything into consideration. And then if you need to cater to the very far right or far left of the curve, then you do a derivative that is more optimal or optimized to these areas.
Just to clarify, in this context, when you say customer, do you mean a big boss or product manager within Intel, or do you mean a Lenovo or a Dell?
Actually, both. So in the client world, our bosses are the client business team at Intel, because we don't go and meet Lenovo and Dell and HPE and every one of them. And frankly, for the client space, the requirements are not unique. They're not that different. They're pretty common. But then when you go to the data center world, you have the hyperscalers, which is AWS, Azure, Google. They all have very different requirements. It's amazing how the cloud world is very different between one and another. And then there's the enterprise vendors that have a different set of requirements, and there we actually meet the end customers and talk directly.
Okay,
Leo, from a channel side or from a client side, the way we're structured is that the client business unit will go out and talk to Dell, HP, Lenovo, et cetera, sure. Collect feedback from the gaming market, collect feedback from notebook users, and then that gets fed into the process that Ori's talking about.
Sometimes they invite us to be flies on the wall, and we listen into these meetings, but we're much less active. We don't actively participate like we do with the data center customers, where they have specific requirements.
So continuing that thought, or me continuing that thought anyway, the type of memory that will be around when you make a particular processor into reality, or the storage, or the type of PCI Express, for you, are these just boxes? It needs to be PCI Express Gen 7 or whatever, and X number of lanes. Is this just stuff to do, like laying bricks on a wall, or is it actually deeply exciting and interesting?
So again, I'm a core person, so I could care less about peripherals and DRAMs and memory controllers and fabrics. I was once a fabrics person. I can talk about fabrics, but not anymore. So yeah, that's the platform guys. They deal with that. SoC guys deal with that. If they need to integrate or LPDDR6 sometime in the future, whatever, that's their problem. As a core person, my only wish is for the SoC not to get in my way, meaning I want that memory fast, high bandwidth, low power. That's basically it.
Yeah, you can think of chip design as multiple teams working on the project. You've got the cores team, you've got the memory IP team, you've got the power team, you've got a bunch of different teams contributing to the overall SoC.
In the conversation with Alejandro, you said you had moved from Fubs, that was the term, a term I must confess I wasn't familiar with, and to big partitions, which seemed to suggest you'd moved from having an awful lot of little bits and pieces you had to nail together into a final SoC into fewer, larger parts. Apart from the fact that sounded like something I thought you'd done 20 years ago, has that changed your working practices significantly, or is that just something you're welcome to move on to?
So yes, it's a different world. Nobody's done that 20 years ago. Well, let me rephrase that. Nobody that runs their part at crazy high frequencies like we do did that 20 years ago. And we went from so a fub is a functional block. Okay, we call them fubs, meaning you have like a cache controller, you have a branch predictor, you have a vector processing unit, these are blocks, functional blocks. And we used to design each one separately and then integrate them into the core. Okay, now if you have like, let's say 300 of those, each one with, let's say, an average of tens of thousands of cells. Now we went to the other extreme where our entire core is like 6 partitions, each one more than 1 million cells. Okay, so it's an entirely different scale, and basically nobody in the industry had design tools that could that had this kind of capacity. Even 10 years ago, I'm not even talking about 20 years ago, and could design that scale to run at the frequencies or operate on the VF curve, voltage frequency curve that we do. So we went to this extreme, and that is an entirely different method of working. It's different tools, different methodologies. It's much more area efficient because the less granular your design, the less white space you have, because white space tends to accumulate on the edge of your block, right? Everything wants to sit in the center in prime location. So when you partition to tiny pieces, you have more white space accumulating on the edge of each piece. Now, if you have less pieces, there's less places for that white space to accumulate, and you can actually shrink to get rid of that white space. So our silicon utilization is way higher than it used to be, okay, which allows us to put more content in each core generation. Our integrations overhead are lower because when you're integrating 6 things versus 300 things, it's easy to see why it's a faster process. And our turnaround time is much faster. Our convergence cycle is faster, which allows us to, it basically allows us to do 3 things. One is be process agnostic, like you talked about earlier, because it's the same design methodology. 2, it allows us to go to market faster because it takes less time to harden that piece of RTL that you want to harden into an actual core. And 3, it allows us to spin off derivatives faster, and that goes to what I explained earlier, where you have your super design that covers 80% of your needs, but then you need to do like special derivative to take care of the super high frequency, high performance market on the right, and then the super low power efficient thing on the left. So So architecturally, all these parts are similar. Same pipeline, same capabilities, same structure, same everything, but you harden them differently to basically accommodate each optimization point. And we've only been able to really do this moving to our new, big synthesis tools and flows.
And you changed that for Lion Cove. So although we only saw that last year, that's presumably you did that 2 or 3 years ago, something like that.
It started basically end of 2020, something like that.
Wow.
That was the transformation, or mid 2020. Yeah.
Hell of a time to be doing it.
Yes.
Nothing else was going on at the time.
Socially distanced and yeah.
Yes. Okay. I was going to mention my terrible £20 headset is a piece of crap. As part of the design, I don't know if you saw Lip Bhutan's keynote from Intel Vision last night.
No, I actually didn't.
But one of the things, well, the timing for you was terrible. Yep. Apart from the fact he was citing any number of areas in which he has personal investments, he mentioned that he wants to use, you presumably, to use an AI design process for products in future. He didn't say when in future, which I must confess made me think of Cadence, which is clearly one of the places he comes from. At the same time, in Lion Cove, which is an existing product, you already have a self-tuning thermal controller that uses AI in the product itself. So do you use AI as part of your design process currently, or are you allowed to talk about it?
I'll say this. We use it extensively, not as extensively as supposedly our new CEO wants us to use it. But we use it. I can really mention two things that are not overly sensitive. One is in our when you verify or validate your design, okay, meaning logical verification. We use AI to sort of minimize the number of tests we run to cover most of the interesting corner cases or validation points. Okay, so you can run like 10,000 tests or 20,000 tests per regression, and that takes time and emits a lot of carbon into the atmosphere. If you can use AI to sort of compact your regression to cover most of your design with less tests, less runtime, less machines, you get a faster turnaround time. We do that. Another thing we do is we use AI to optimize our synthesis, meaning you can bias the synthesis to be either more performant or more power aware. And there are AI tools that allow you to optimize your place and route to achieve your bias, meaning optimize for power versus for frequency, for example.
Are these Intel tools or tools you buy in?
Most of our tools are supplied by external vendors, but the flows we use have a lot of hooks that are added on internally. So the recipes that we use are Intel recipes, most of them that are all industry standard, but are tuned to our needs in cooperation with our vendors.
Okay.
So if you go to other customers, they don't run the same, other companies, other CPU manufacturers, they don't run the same flows that we do.
Okay. And SMT. So you've ditched SMT in Lion Cove, which means the number of cores is the same as the number of threads.
Yep.
Is that actually a simple thing to do? I mean, it sounds like actually it's really simple. You take out some stuff and now you've got less stuff to work with.
That's a very simplified way of stating it. Yes, you take out stuff, but the challenge is not taking out the stuff, but redesigning the core to be optimized for single thread. So just deleting a bunch of logic or taking away a bunch of transistors, we wouldn't have done it if that's all we got out of it. We designed a brand new core that is way more efficient and way smaller, okay, due to the fact that we removed SMT. And that's actually where most of the benefit comes from, because we are more area efficient and we're more power efficient due to the fact that we don't have SMT in this core. And actually, I scribbled down an example of what SMT removal gives us before the meeting. So I can just pop it up and share if you'd like.
Yeah, absolutely, definitely.
So there's two things that explain the benefit of SMT removal. So here, this explains the PNP aspect of it. So I'm measuring IPC, which is instructions per cycle, which is a proxy for performance at ISO frequency. CDINE, which is a proxy for power and area. So when you have an SMT core, SMT capable core with SMT off, that's our baseline. Like everything is one. Okay. Now, when you turn SMT on this core, you get 30% more performance for 20% more power. Okay. Obviously, same area because it's the same core, right? So what we've done is we've taken SMT out and we've optimized our design to be for ST. So we have the same IPC, okay, because it's the same single thread running on the same microarchitecture, but we saved roughly 15% area and 15% power in this core. So how does it stack up? Okay, so when you're measuring perf per power, and you're comparing this ST optimized core versus an SMT capable core with SMT off, you come out ahead because you're basically, you get the same performance for less power and less area, right? And when you're measuring your performance per power per area, which is how efficient is your compute given a certain area in silicon, you come out way better, like 40% better. But that's expected. That's not a big deal. The big deal is how we stack up versus the SMT core when SMT is on. Now, it turns out we still come ahead in terms of perf per power. Okay, 8.5% ahead. So these are made up numbers because it depends on the applications, how benefit SMT is per the thing you're running, but this is like an average or a rule of thumb. Okay, we also come out ahead in perf per power per area. Where we're lagging with this core is thread density, meaning for a certain amount of area you have more performance, all else being equal, okay, with an SMT capable core.
One of the things you said in conversation with Alejandro was that this would also give you a benefit, and you said future expandability.
Right. So SMT is a complicated feature. It's complex. It is hard to keep scaling it and in an appropriate manner. It has drawbacks, meaning you need to make sure you don't run into like security problems because there's stale data that has to be cleaned up. There's a lot of housekeeping to be done on an SMT capable core, so it won't be exploited for side channel attacks. It requires maintenance. Okay, and so if you have an ST only core, you can really your cadence of architectural improvements can be faster than if you have to take care of not breaking anything SMT related. Okay, so I know that it allowed us to move faster in per thread performance once we've ditched SMT than having SMT still around. Now, having said all that, and again, this is a client-centric conversation. In the data center world, where all you have like is P cores and not E cores, we still have SMT because, for cloud providers, their entire TCO, total cost of ownership model, requires thread density. And as you see here, thread density still likes SMT. So one more thing, which not everybody understands, but I like to show, is how SMT allows you to scale, right? So let's say you have a workload, a really big workload that's 95% parallel and 5% serial. Okay? So you would think that SMT is great there, right? Because it's 95% parallel. But let's see what happens when you have 8 cores. So when you have 8 cores, you really divide the parallel work into 8, right? But the serial part remains the same because it doesn't care how many cores you have. It's still 5% of the work. Okay? So by scaling up the number of cores, you get a nice speed up. Okay? It's 17 versus 100. Now, what happens when you invoke SMT? When you invoke SMT, let's say you get a 25% speed up for the parallel work. Okay? But you also get a slowdown for your serial part because you have one thread that has to utilize half a core because the other thread is spinning in a pause loop. That's what happens when SMT is enabled. So SMT is not only how fast you can run, but also how efficiently you can wait. So let's say we only have a 20% slowdown when the other thread is idling, doing nothing. So this 5 turns into 6. So SMT is still okay when you have 8 cores, but what happens when you scale up to 32 cores? Using the same math, SMT actually slows you down. So the more cores, physical cores you have, SMT actually gets in the way of your ability to parallelize and shorten the time because you always have a serial part. Always. There's nothing that is entirely parallel.
Does that apply regardless of whether we're talking P cores, E cores, low power E cores? This
is simple software
universal truth.
engineering.
Okay.
I mean, when you have more cores in the system, SMT slows down your serial part more than it speeds up your parallel part.
Okay.
So when we had 1 core per socket or 4 cores per socket, SMT was a big deal. Yeah. Now that most of our sockets have 8, bare minimum 8, but mostly more than 12 or 16 cores, SMT kind of loses its appeal. And that is even ignoring the power situation where, SMT off, you can run the thing at higher frequencies because you can utilize all of your power envelope. So this is something that most people don't have a grasp of. They see, our current products, SMT on versus off, but they don't see the opportunity cost, right? The other side of things. So
does this suggest
is really important, Leo?
Yeah,
if I may just draw a connection back to your readership, what we're really angling for here is an overall speed up in single thread performance, an overall reduction in the amount of time the core spends waiting, and better multi-thread scalability by preferring E cores to SMT. We think we can get to extremely high core counts in client space with this approach without using SMT. It will be more power efficient. It is safer from a security point of view. And we think it offers better scalability for the client market overall.
And you also
that the era of SMT is behind us.
Yeah, and you also get predictable performance, meaning SMT is kind of a box of chocolate, so to speak. If both threads are low IPC, consume different parts of your compute, then they play well together. But if both threads are high IPC and can utilize the entire core, SMT doesn't help you. If both threads are DRAM bound, SMT doesn't help you. If both threads thrash each other because the cache is too small, it doesn't help you. So the thing where, games, for example, games need predictable performance. You can't get, and that's why most games or most gaming apps turn off SMT because they want that predictable performance. They don't want to leave it to chance which of the gaming threads bundle together on the same core.
This is a great point. So what is not widely known in gaming, Leo, is that games actually set their own core and thread affinity. It's called an affinity mask. It has some assistance from the operating system, but more often than not, games actually make their own thread scheduling decisions. They're programmed that way by the developer. And so many times when gamers report, hey, my game is faster if I turn SMT off, yeah, it's been like that since the Pentium 4, actually. And this is, to Ori's point, this is a real case of SMT often leading to predictable and negative results for the client market.
With SMT off, does Thread Director still have about the same amount of work to do, or does that
Yes,
change?
absolutely. No.
Certainly.
Thread
Certainly.
Director has a lot of work to do because it differentiates per power envelope or per situation where it's best to run a certain thread. And the answer can be different based on the scenario or the workload or the situation, the power situation.
Do you find do you ever test these days on Windows 10, or is it only ever Windows 11 for you guys?
Actually, we're
Windows 12, go for it.
no. I mean, we don't really. We test on Windows, we test on Linux, we test on a lot of things, right? So we're not really optimizing for a certain OS. We're optimizing for applications. The OS For the OS, we do things that are specific to the environment, such as different paging capabilities, different page tables, TLB sizing, etc. So we want to make sure that we utilize or have the best paging scheme for Linux, best paging scheme for Windows, but we don't really optimize performance for a certain OS. We optimize for application level.
Okay, thank you. We're about on the half hour. I have a final question which might be completely outside of your areas jointly. Again, harking back to Lip Bhutan yesterday, your CEO. He said quantum computers are coming sooner than we think. He didn't say what we think, so he didn't say how much sooner that might be. And everything always seems to be 10 or 20 years away. Is this something about which you have any thoughts whatsoever, or is this wholly outside your area?
Completely out of my circle of competence.
I can't argue with that. In which case, I'll take that last piece out. What obvious question?
We're still Newtonian over here. We're not. We haven't made that leap.
You know, the thing about quantum computing is that it's a good tool for certain jobs, but it's not a general purpose tool. Quantum computing is awesome if you want to very quickly sort through a huge basket of numbers, like incomprehensibly large numbers, and you're quickly trying to whittle that down to something useful. Cryptography is a great example here. You have a bajillion permutations. You're trying to figure out the answer. Good for that. But as general purpose, you know, you're probably never going to see any of us on this call talk about quantum computing.
Grand Theft Auto 6, yes.
So certain governments have certain requirements for us to look at post-quantum cryptography acceleration in our parts. So we do improve our algorithms and put in specific hardware for certain requirements in the post-quantum world. But personally, I am not dealing with quantum compute outside of these very specific requirements.
Could I finish up with, it's not exactly a question. It's harking back to when I was in Israel in 2022, and the discussion at that point was Golden Cove to Raptor Cove. So in your context, that's 1,000 years ago. And Isaac Silas, I've probably butchered the name, was talking on stage. And it essentially was saying you'd had to conjure up Raptor Cove from nothing because you had to extend the products by a further year. So you've got no budget, make this thing better out of nothing, was approximately what he was saying. You added some E cores, but the P core sounded like it was pretty much unchanged, and yet somehow Intel managed to find, or you guys found, about 20% improvement.
Yeah, it's okay. So the P core was not unchanged. The P core did what we call a PV push or a speed push, meaning we could tweak the design to hit a higher frequency at the same power level. Okay, and there were also some process that was still 10 nanometer, 10 plus plus, if I remember correctly. There were also some process tweaks that went into there. So it was a combination of tweaking the design in conjunction with process improvements that allowed the Raptor Cove core, although being the exact same microarchitecture, exact same RTL, to run faster than the Golden Cove core.
And you're talking double-digit percentages. I mean, you've added
Yeah.
E-cores, which was about 20%, but the P-core improvement was around 20%, which...
No, it wasn't 20% P&P. It was 20% peak, but not at the same power.
Thank you. Okay. Was that something that you guys over there could have done in the first place, knowing everything you knew, and basically by fixing things and tweaking things? Or did it require you to have the first generation of Golden Cove before you could come back to have another go at it?
It definitely required us to have silicon in our labs, high volume, to basically understand where our bottlenecks are in the design. And again, it's all about time to market, right? I mean, if you have a 6.2 gig part ready to ship, you won't keep it in the house just to hit 6.4 gig a year later, right? So, it's when you iterate, you get a better result.
A perfect note to finish on. Thank you very much for your time, chaps. Is there anything I need to have covered that I haven't covered? Any obvious question I should have asked?
Not an obvious question. I just like a commentary in general. I still run into enthusiast users who are kind of like shocked and dismayed by this SMT deprecation. They just don't understand it. And I get it, right? It's been around for 20 something years in our designs. And that's a big change, and people are still coming to terms with that.
Yeah.
But like for the stuff that the client market cares about, single thread performance, gaming performance, scalability of multi-core, multi-thread, this is a very direct and positive development. It's like all upside for us. And so like if I could ask you to carry anything forward, we're completely convinced of that. We think this is the right thing to do for client.
Perfect. Gentlemen, thank you so much for your time. It's been an absolute pleasure having you. Thank you very much.